interesting happened in my astronomy life very recently. Um, Way back in the 1980s, I'd go over to the Lunar and Planetary Laboratory in Houston over on Bay State Boulevard near the Johnson Space Center, and I would pore over the lunar orbiter photographs that they have archived there, the big 16 by 20-inch prints that were used to map the moon and chart all the Apollo landing sites. Well, like most things NASA, eventually they get tired of the toys and they throw them away. So the Lunar and Planetary Laboratory was going to scrap these uh, lunar orbiter archives, throw them away. But the troops down at the Corpus Christi, Texas Astronomy Club salvaged the entire bunch. And I now have in my possession several 100 pounds of these giant, huge lunar orbiter photographs, the very same ones that were used to plot the Apollo program. Many of these have scribblings on them, coffee stains from folks poring over them. So these are real pieces of history. And for somebody who loves the moon as much as I do, to have these in my possession now it's just phenomenal. But see if I can go to full screen here. Hopefully you are now seeing my title slide is full screen, Postcards from the Moon. The whole premise of this, it's been a half century since Apollo, and much has appeared in the media about how we got to the moon, the politics of why we went to the moon, and the personalities who engineered, directed, and actually flew the Apollo missions to the moon. And I have to brag, I got a message on Facebook 2 days ago from Fred Hayes, Apollo 13 astronaut, telling me that he was enjoying my new book about the moon. Push the right one. But in the half century since humans set foot on the moon, really, how much does the average person know about the moon? Well, surprisingly little. And I'm kind of making it my mission to reacquaint the amateur astronomy community with the moon. We've been ignoring it. Deep sky is king. Deep sky astrophotography, chasing the faint fuzzies, but the moon has always been there, uh, uh, waiting for us to come back. I've been in love with the moon my entire life. My earliest memories of the moon were watching moonrise through my bedroom window when I was a child. And today, over 70 years later, space age explorations have not stripped the wonder and the mystery that I felt for the moon when I was young. Now, there's an actual name for people like me, and it is not lunatic. I am a selenophile, a person who loves the moon. And I hope after you get to know the moon a little bit better, after you see my presentation, you too will be a selenophile. Matt, in his introduction, mentioned that I have published a number of astrophotography books. That's how I'm best known in the astronomy field. In 2000, Whitefield Astrophotography came out. It was well received, but photo technology changed, and it was the last book written about film-based astrophotography. So I came out with Introduction to Digital Astrophotography, which was the first book written about astrophotography with a DSLR. Now, in spite of my lunar photography that most people know me about through on Facebook, I still enjoy deep sky astrophotography. I have a Celestron 14 with a hyperstar, which is on an observatory on top of my garage out in the backyard. I remotely control it from right here at this desk. And I'm able to, with the amazing filters we have nowadays, take these astrophotographies from the middle of a city of 2 million people. So the hyperstar laughs at the moon. I'm able to photograph sharpless objects 30 degrees away from a full moon using this system. So the moon and deep sky are within my reach now, just from my own backyard. But continuing on, in 2006, I published Introduction to Webcam Astrophotography. Now, this book helped popularize the use of webcam video capture for planetary photography, particularly lunar photography, like I do, and I think it helped launch today's planetary camera industry by demonstrating the viability of using such photographic techniques. My pictures of the moon have appeared on the covers of magazines, have appeared in magazines, sometimes in articles that I even wrote, appeared on the covers of various books. If you have Turn Left at Orion or the latest Backyard Astronomer's Guide, all of the moon pictures in the Backyard Astronomer's Guide are mine. Now, over the past 20 years, I've spent an inordinate amount of time chasing large telescopes across the southern United States in order to take high-resolution lunar photographs. But the irony is, I find that I can take better images of the moon from my own observatory in my own backyard with a 7 to 11-inch telescope, because the poor seeing does not degrade the image in the smaller telescopes as much as it does the big telescopes. 24-inch telescope, you're at the mercy of the seeing much more than you are with a 7-inch Maksutov. Now, how good is modern lunar imaging with a modest telescope? The image on the right is a plate from the famous Kuiper Lunar Atlas. It was the best professional astronomers could do from the Earth. Now, this is before Lunar Orbiter, back in the 1960s. And the image on the left was taken from in my own backyard with a Celestron 11 and a planetary camera. It's the same field of view, except mine is north up and the Kuiper Atlas is south up. But I'll let you be the judge. Which one is best? I think the amateur astronomer nowadays is out shooting the professional when it comes to lunar photography. Now, I definitely say that I do not have any special talent. I'm not a degreed, trained researcher. I only claim that I am passionately curious, and I just have the tenacity to keep at it until I figure it out. Now, the moon is my playground, and tonight I invite you to come out and play with me. Now, when I was young, the moon was a big deal. This is back in the heyday of Apollo. The moon was a dream. It was a goal, a destination, and a place of mystery to be explored by brave heroes who dared to set foot on another world. Then in the 1970s, there was a fundamental shift in amateur astronomy. The introduction to the 8-inch Schmidt-Cassegrain gave us a powerful, affordable, and portable telescope that opened up the deep sky to amateur astronomers. The moon kind of faded from our amateur astronomy scene. But my goal in this presentation is twofold: to bring the moon back within our astronomical realm, to make it not something to be avoided because it interferes with the deep sky, and to get you not to just to look at the moon, but to see it and understand it. Now, today, many astronomers consider the moon boring, a place covered with bumps and holes, but the moon is not visually static. The moon is a geological wonderland that changes day by day, even hour by hour. And there is much to see on the moon once you know what to look for. So I want you to go back to the moon with me tonight and rediscover its wonders. So we're going to look at the creation of the moon, the evolution of the moon's face, understand the various forms of lunar geology, and then we'll explore a couple of sentimental lunar favorites. Now, the earliest event on the moon, of course, was its creation. And current thinking is that the most popular theory is that shortly after the creation of the solar system, another planet was in the inner solar system vying for orbital supremacy with the Earth, and eventually it lost. Earth and this hypothetical Mars-sized body that we now call Theia collided, shattered the impactor, crumbled most of the Earth, the proto-Earth, and showered all of the material in this cloud, Saturn-like ring that surrounded the Earth. And within a matter of days, and possibly within a year, the body of the moon formed, coalesced out of this debris that was shattered from the explosion, the collision. Many computer models have been run on this, and invariably, in a collision like this, the Earth we understand today forms, and a moon, sometimes two moons, form as well out of the debris cloud. Now, the early molten moon, um, the science fiction scene of a glowing sphere of molten rock flying through space notwithstanding, the early moon was probably a dark body, had a chilled skin of solidified rock on the surface, insulating the molten interior, and it took millions of years for it to cool down. And during this time, iron and the heavy radioactive elements sank to the middle. Global uh, magma ocean was formed, and the light elements, the silicates, floated up to the surface. Now, once the moon solidified, um, Matthew will appreciate the analogy. He's the dinosaur guy. You know, back when we were kids, we were all fascinated with dinosaurs and knew about the various geological epochs that Earth went through, the Triassic and the Jurassic and the Precambrian era and so forth. Well, the moon has a similar geologic time period. Once it's solidified, it was in the pre-Nectarian epoch. This is before 3.92 billion years ago. And then from 3.92 to 3.85 billion years ago, the Nectarian epoch occurred. This is the period of the late heavy bombardment when the Earth, all of the inner planets, were heavily bombarded by asteroids that were dislodged by the Jupiter and Saturn entering a 2-to-1 gravitational resonance, which shook up the entire solar system for about 100 million years. After that, we entered the Imbrium epoch up to about 3.1 billion years ago. And during this time, extensive volcanism occurred on the moon. The dark maria formed and filled in the basins that were blasted out during the late heavy bombardment and created the face of the moon. The Eratosthenian epoch picked up after that and extended up to about 1 billion years ago. And this is where a majority of the post-Mare formation cratering occurred. And then we entered the Copernican epoch, the modern era, about 1 billion years ago to the present. And uh, any crater that formed on the moon during this period of time can be identified because it still has a ray structure. Rays fade after about 1 billion years. So the lack of crater rays will date a crater as being in the Eratosthenian or earlier epochs. If it has rays, it's going to be a Copernican. Now, the early moon looked very different than what we see today. During the Nectarian epoch, no volcanism yet. The basins have been blasted out. The moon's crust was solid. The impact rate was about 300 times higher than it is today. Then during the Imbrium epoch, we underwent about 1 billion years of volcanic flooding, slowly filled in the deep basins and created the Mare that we see today. And finally, the modern epoch, the Copernican epoch, we see the modern moon. And if there is like I said, if there is a crater with rays around it, it formed during this modern Copernican epoch. Unfortunately, there was a significant reduction in the crater forming rate, which is a good thing because the Earth got the same blasting that the moon did. Mars did too, Venus, Mercury. Mercury looks very similar to the moon with all the impacts. If the crater formation rate had not slacked off, we wouldn't be here. There would be mass extinction after mass extinction, and humanity could have never been established. So be grateful that things calm down. Now, there's two primary landscape forming processes on the moon: volcanism and impact cratering. So everything we see on the moon is either the result of an impact or subsequent volcanic modification of something created by an impact. So the most obvious things that we see with the naked eye, the lunar maria that form the face of the man in the moon. These are fields of dark basalt that deposited in these basins, giant craters that formed during the Nectarian epoch. And we have to understand that the maria and the basin that they lie in are not the same thing. They're created by two different things. The basins were created by asteroid impacts, and the maria were formed by volcanic eruptions flooding into the basins. And not all basins contain a maria. There's 70 something known basins on the moon, but only the ones on the near side that are well below mean lunar elevation filled in with basalt and created the face of the man on the moon. Now, the maria, they define the caricature of the man on the moon, and there are 21 named maria on the near side. There's 2 on the far side, very small ones. 11 were named in the 17th century by Giovanni Riccioli, the classical ones that create the face of the moon, man on the moon. 8 more were named in the 19th and early 20th centuries, and 2 were named during the space age. The last one being Mare Insularum, just under between Kepler and Copernicus crater, named in 1976. Now, the recurring theme with the Maria is they are circular. Mare Nectaris, or round. Mare Crisium, it looks egg-shaped because of our perspective. Serenitatis, again, looks like a big giant Easter egg. Imbrium, round. These are gigantic craters that filled with lava. So they're going to be basically round. Now, Humorum, same thing. Now, Oceanus Procellarum is the largest of the Maria by a factor of 2, twice as large as Mare Imbrium, but it's so foreshortened on the western hemisphere near the limb that it really doesn't even contribute to the caricature of the man on the moon. And not all basins completely filled in with basalt. The Austral Basin down in the southeast limb is close to the far side, which has a thicker crust. The proximity to the thicker crust far side restricted volcanic eruptions, so Mare Austral ended up being a collection of lava-flooded craters and not an entire lava-flooded basin. And then, of course, not all maria lie within a single basin. Mare Frigoris, which kind of forms the man in the moon's eyebrows. It's 1,800 kilometers wide, but only 200 kilometers high. It lays in portions of the Procellarum, Imbrium, and Serenitatis basins. Now, mountains on the moon, fundamentally different than those on Earth. Earth's mountains are continuously created by plate tectonics, volcanism, and are eroded by Earth's weather and oceans. Now, lunar mountains were created by an entirely different process, by an asteroid impact. Lunar mountain chains are the raised rims of impact basins. Individual peaks can also form at the center of large craters as a function of how the surface rebounds from the shock of an asteroid impact. But lunar mountain chains are all the rims of impact basins, and they have been unchanged since their formation almost 4 billion years ago, whereas Earth's mountains can be significantly altered within only 100 million years. Popular mountains on the moon, the Alps Mountains east of Plato, bisected by the Alpine Valley. Continuing around eastern side of Mare Imbrium, the Caucasus Mountains. All mountain chains on the moon are named after terrestrial mountain chains. The Apennine Mountains, and then down south, just above Copernicus crater, separating Copernicus from Mare Imbrium, the Carpathian Mountains. Some mountain chains on the moon you can only see one day a month or one day during the lunation. The Cordillera Mountains surrounding Mare Orientale on the western limb. This picture is turned sideways, so it'll fit the screen better. These are on the extreme western limb. They're in shadow until the day before full moon. And on that one day before full moon, the shadows being cast by this mountain chain allows us to see them. And well, we see them in the foreground, and then near the horizon, we see the twin mountain chains of the inner and the outer Rook Mountains. These are the three circular impact basin rings surrounding Mare Orientale. Then we go a day later during the full moon. It is so flatly lit that the shadows disappear, and we no longer see these mountains. So the Cordillera will appear only one single day per lunation. Uh, Other mountain chains, the Jura Mountains surrounding Sinus Iridum up in the northeast corner of Mare Imbrium. And not all mountains on the moon have a name. There's a very prominent mountain chain on the western side of Mare Crisium, but they have no name. There's a lot of major features on the moon, and I have lobbied with the head of the IAU Lunar Nomenclature Committee to get some of these named, but I don't have enough horsepower. I lose. Now, types of craters on the moon. They're not all just holes in the ground. Um, Craters are classified in a crater main sequence, not quite as extensive as the name that we borrowed from stellar astronomy, the main sequence of stars, but there are three different types. Below about 16 to 21 kilometers in diameter, the impact dynamics will simply excavate a simple bowl-shaped crater. Looks very much like scooped out with a giant ice cream scoop. Above that size, so above 16 to 21 kilometers, the dynamics of the impact will create a raised central peak, and the outer walls will collapse and crumble down into the crater in a series of terraces. Now, above 300 kilometers in diameter, we now classify it as a basin, and it's no longer a crater. It's a separate class of feature. Examples: on Mare Imbrium, Helicon and Leverrier near Sinus Iridum, simple craters. A very famous example of a complex crater, Copernicus. We're looking right down its throat. And a basin that did not fill up with basalt and become a maria, Bailey, down on the southwestern limb of the moon. Complex craters, like I said, they feature a central peak and collapsed terrace walls. Examples: Pythagoras up in the northwest, Moretus down south near the South Pole, Geminus up north of Mare Crisium, and crater rays. I've mentioned that they fade after about 1 billion years. They're made of pulverized glassy material thrown from the crater by the impact that the impact explosion that created the crater. And crater rays are brightest near the full moon. That's because the glassy material that makes up the rays it reflects light very similar to how uh, highway signs do. You've all driven down the interstate highway, and your car headlights shine on a sign way ahead of you. You can easily read the lettering on it being reflected back at you, but you can't even see the sign itself yet because it's so far away. Now the crater rays do the same thing. They reflect the the light rays directly back toward or they're most efficient at reflecting directly back toward their light source, which is the sun. And of course, at full moon, Earth is between between the sun and the moon, so crater rays are brightest during the full moon. The Tychonian ray system is the largest on the moon, spanning about 2,200 kilometers. But there is a mystery with Tycho. Notice that the railroad tracks extending up to the northwest, uh, they're parallel. They do not converge on Tycho. And then there's this strange rogue ray heading down to the southwest. It's tangential to Tycho's rim. And if he can figure out why, you got your name on a good research paper. Now, monodirectional rays, such as those extending from Messier and Messier A, on Mare Fecunditatis, and butterfly ray patterns like extending from Proclus just west of uh, Mare Crisium. These are an indication of a very oblique impact. Uh, Extremely shallow impact. I mean, less than 5 degrees. No ray material splashes back in the direction that the impactor arrived from. Now, secondary craters are another class of array craters. These are created by the impact ejecta thrown from a primary crater's formation. Secondary craters are shallow because their impact speed cannot exceed the 2.4 kilometer escape velocity of the moon. If something is blasted out of the crater by the asteroid impact traveling faster than that, it escapes the moon and enters solar orbit. So secondary craters often lay in linear chains, as we see radiating out from Copernicus. And the majority of craters on the moon smaller than 20 kilometers are believed to be secondary craters, but these can appear hundreds of kilometers from the primary. So it's tough to associate them with them unless they're in distinct patterns like we see here surrounding Copernicus. Now, not all craters are round. Um, Hazel is peanut shaped, but it's the chance overlap of two circular craters. Ray to E, well, it's kind of keyhole shaped. It's also the result of multiple impacts. But Schiller is another case. Schiller is a single oblique impact that plowed this channel down the face of the moon, and it is so large that if you substituted a circular crater diameter for the length of Schiller, then Schiller would be one of the 10 largest craters on the moon. And more not round craters, Anaximander A and B, form the heart shape up on the upper left. Meton, uh, 4 overlapping craters that have had their interior buried by basin ejecta, so you can't see the inner portion of their rims. It forms this 4-leaf clover shape. And then, of course, Agrippa and Godin look like a kind of bullet-shaped, bell-shaped. There's hexagonal-shaped craters. There's octagonal-shaped craters. There's even square-shaped craters. So not all craters are round. Then there's another class, the floor-fractured craters. These are craters that were modified by subsequent volcanism, not lavas that overflowed the crater from the outside, but lava that welled up from under the crater and uplifted the floor, sometimes flooding the floor, but always creating the series of rills, cracks within the crater. Thus the name floor fractured. Gassendi, very famous example, Posidonius up on Mare Serenitatis. Atlas crater up above on the northeast. Yet another class of craters is called ghost craters. These are craters that existed in a basin before it flooded with lava. The lava flooding paved over the floor of the basin, and if the crater is big enough, now just the crown of it protrudes above the basalt. Flamsteed P, 100 kilometers in diameter. All we see is the very rim of its sticking up above the lava. The same with Stadius near Copernicus, but Stadius is kind of hard to spot because it's lost in a sea of secondary craters. Lamont, just north of the Apollo 11 landing site. Not just a ghost crater, but a ghost basin. It's a double impact ring, so we call that it's definitely a basin with the double impact ring buried under the basalt. Crater chains. The easiest explanation of how these chains of craters came into being, Catena Mueller, Catena Davy, Catena Abulfeda at the bottom, the longest one, over 200 kilometers long. The easiest way to explain it is to hop into the Wayback Machine and go back to the 1990s when comet Shoemaker-Levy 9 slammed into Jupiter. We saw how the comet broke up and rained down onto Jupiter in a sequence of impacts. The same thing happened here. Uh, the Earth-Moon gravity system broke up an object, and it sequentially rained down piece by piece, creating a linear chain of craters. Another feature on the moon, volcanic, are wrinkle ridges, and these are known by the scientific name of dorsum or dorsa, and these are folds in the Mars surface where the sheets of basalt have crushed and buckled together. Uh, this happens as the basalt slumps toward the center, the depressed center of a basin, and uh, they pile up against each other, creating these ridges that are only several hundred meters in elevation, but they can be hundreds of kilometers long. Uh, these wrinkle ridges are typically named after Earth scientists, and the most popular one is what we call the Serpentine Ridge on eastern Mare Serenitatis. And this is a combination of Dorsa Lister and Dorsa Smirnov. They kind of rope together and create a continuous uh, one long wrinkle ridge that's almost 400 kilometers long. Other wrinkle ridges over on western Mare Imbrium, Dorsum Heim, extending south from Sinus Iridum. And then there's unnamed wrinkle ridges that look like frozen ocean waves washing into the horseshoe bay of Sinus Iridum. And had mentioned many features on the moon remain unnamed. The very prominent wrinkle ridges in the middle of Mare Humorum bear no name. Now, another feature on the moon, is also of volcanic origin, are the rills, scientifically known as a rima or rimae in the plural. These are grooves or channels on the moon that are appreciably longer than they are wide. Now, these are formed by three different processes, but they're all volcanic. The linear rills are formed um, by the land slumping between two parallel faults. Now, this happens when the crust is split apart by a volcanic dike or a sheet of magma that pushed up vertically from the core of the moon, but it did not breach the surface as an eruption. It merely split the surface. And Rima Hesiotis at the bottom, an example, Rima Sursalis over southwest of Oceanus Procellarum. These are very long. The Sursalis rill goes almost 400 kilometers. Now, arcuate or curved rills are created by the stretching of the land near the edge of a maria. Remember, I mentioned that wrinkle ridges are caused by the basalt slumping toward the middle of the basin. Well, as that basalt slumps toward the middle, it stretches the shoreline and pulls apart these rills. And here we see the Harpalus rills arcing around eastern Mare Humorum. Almost looks like a giant cat scratch on the moon. Now, sinuous rills are formed by flowing streams of lava, much like channels are cut in the earth by flowing water. In this case, Hadley Rill on the between the Apennine Mountains and Mare Imbrium, the Apollo 15 landing site. At one time, flowing lava flowed through this channel, eroding it, enlarging it as the lava flowed. Another feature on the moon, or we call them scarps. Scientifically, well, a scarp is basically a steep slope. Scientifically known as rupas, and they're formed by two different processes. Some scarps are the surviving rim of an impact basin, such as Rupus altai that we see here, which is about a 400 kilometer long segment of the outer Nectaris basin impact ring. It is the only surviving segment of it. The rest of it has been destroyed by subsequent impacts. And the other types of scarps are created by the slumping of land on one side of a fault, such as the lower feature here, Rupus Cauchy. The upper one, Rima Cauchy, is a rill. The lower feature is a scarp. a slope, and notice the little volcanic domes down south of it, one with a little caldera on it. The most famous of the lunar scarps is straight wall, Rupes recta, on the western Mare Nubium. That's one of the sentimental lunar favorites that everybody loves. And past volcanic activity on the moon is evident in the form of pyroclastic deposits, sinuous rills, ash deposits around cinder cones, and volcanic domes. The most famous of the sinuous rills, Schroeder's Valley on the Aristarchus Plateau. The heart-shaped pyroclastic deposits north of Rima Hygitus, another volcanic feature. The shallow mountains, only about a kilometer, about 10,000 square kilometers, but only about a kilometer high, noticeably darker in color because they were dusted with volcanic ash blown out of the volcanic vents that dot along the Hyginus Rill. And volcanic cinder cones on the moon, some of the easiest ones to see are within Alphonsus crater. Look at the 9 o'clock, 12 o'clock, 3 o'clock, about the 4:30 or 5 position. You see these noticeably darker spots. This is where volcanic ash spewed out of a cinder cone, and the ash is still there. We can still see it. Now, volcanic domes on the moon are bubble-like swellings or small shield volcanoes where highly fluid lavas formed low pancake-shaped structures. Now, volcanoes on the moon do not build up into these Vesuvius-like steep cone-shaped volcanoes like we have on Earth. On the moon, the flows flowed out, flattened out, made pancake shaped structures. The most famous are the Marius Hills on Oceanus Procellarum. At the right time of the month, when they cast a shadow, you can see them just like dimples all over that area of the moon. And then a day or two later, when the sun is higher, the shadows are gone, you don't see them anymore. And of course, Mons Rumker up on northern Oceanus Procellarum, collection of volcanic domes on top of a elevated plateau about a half a kilometer high. Anybody who looks at this in a telescope can see this is an elevated structure, but Rumker didn't get the respect it deserved for several centuries. It was misclassified as a crater, but anybody can see that it's a protrusion, not a hole in the ground. Now, going to look at some sentimental lunar favorites. Now, a novice will quickly fall in love with several things on the moon. Plato crater, Tycho crater, straight wall, Copernicus crater. Well, these features are so classic and endearing that even the old timers like me come back to them again and again. Plato crater is distinctly different. It looks like it's been paved over, flatter in a parking lot. Lava welled up from underneath. It did not become a floor fractured crater, but it completely smoothed it over. The lavas within Plato pushed up almost half a kilometer higher than the lavas in in Mare Imbrium, just to the south. Like I said, Plato is just north of Imbrium. Mare Frigoris just above it. Cassini crater down south below the Alps mountains. And I had mentioned earlier a square crater on the moon. There it is, W Bond. The northern and western and eastern rims almost look like the ramparts in an old army fort. Look like fortifications. Very unusual shaped crater. Getting closer to Plato, nested in the Alps mountains. If you pick up those 4 little craterlets on the floor of Plato, well, enjoy it because you're having some good seeing that night. Oops, come on. Pico crater, Pico, Mount Pico, Mons Pico below it, and Mons Python, little peaks protruding from northern Mare Imbrium, and they take on a whole personality of their own. People people are endeared to these. They just love these little features. And then down here on the bottom, notice the hammer shape. I call that Thor's hammer. And Agent Coulson can quit looking. We found it. It's been under our nose all this time. And even closer to Plato, now we clearly see those craterlets on its floor, and close up of the Alpine Valley cutting through the Alps mountains. And if you can spot that rill running down the center of the Alpine Valley, you've really got some good seeing going that night. That rill is only a half a kilometer in diameter, half a kilometer wide, but it's lengthy, so we can see it. Tycho crater, another favorite. Not one of the bigger craters on the moon, but it's got that ray system that stretches all the way across the southern hemisphere. So Tycho is very new, very fresh, only 108 million years old. It formed during the dinosaur era. The blast that created Tycho most assuredly startled a T-Rex. There's no question about it. And then the curiosity is the other craters in the area, Longomontanus, Clavius. Whoops, pushed too many buttons. These craters surrounding Tycho are almost 40 times older. These other craters are pre-Nectarian, over 4 billion years old. And then here's Tycho nested in the middle of them. And a close-up of Tycho, here, look in the immediate area around it. Notice the thousands of tiny little pits. Those are created by secondary craters by the blocks of material blasted out of Tycho when the explosion formed the crater. And another view, you can still see this hundreds and hundreds of secondary craters scattered in all directions. Copernicus crater is another sentimental lunar favorite because it also has a huge ray system, but we also get to look straight down from above and see its entire terrace structure, the central peak, the radiating secondary craters spreading out in all directions. And Copernicus even puts on a good show at sunrise or sundown. At this time, the rays aren't very prominent because, like I said, the rays are brightest near the full moon. But there's so much detail in the area. We're just south of Mare Imbrium. Oops. Eratosthenes crater nearby, the Carpathian Mountains, the secondary craters surrounding Tycho, Mare Insularum, the newest of the lunar seas, named just in 1976, named because you see all the dozens of hilly protrusions protruding above the Mare surface. It looks like islands on a sea, thus Mare Insularum, the Sea of Islands. And then just for artistic effect, we threw Reinhold crater down there. Straight Wall, another sentimental lunar favorite, and located on western Mare Nubium. Arzachel crater up above, one of the other sentimental lunar favorites we're not talking about, but you will become familiar with it if you become very familiar with the moon. It will be one of your watch craters. Thabit crater, nothing special about it except it's the only nearby named crater. So we follow the Horseshoe Bay. Here is the eastern rim of a crater, but follow the wrinkle ridges that mark the buried western rim of this crater that were sunk underneath the basalts. So this partially buried ghost crater, it has no name, but it's among the largest craters on the near side of the moon. So we unofficially call it Ancient Thabit in a nod to Thabit crater right next to it. Now, sunset on Straight Wall. Here, part of Straight Wall is already in shadow, but the very ridge of it is still catching the last rays of sundown. Imagine if you're standing on the rim of straight wall looking out westward across Mare Nubium as the sun sets on the horizon and goes down. Consider the moon rotates a lot more slowly than the Earth. It takes almost a month for the moon to go around once. On Earth, as soon as the sun touches the horizon, you can set your watch. 2 minutes later, it's gone. On the moon, sunset would take an hour to fully disappear. So the view would be quite spectacular. And we're going to wrap up this by cruising around some nicknamed features on the moon. Now, we're all very familiar with deep sky objects that have very familiar names, the Lagoon Nebula, the Swan Nebula, the North America Nebula. These all have catalog names and numbers and so forth that are official, but these unofficial names are how we know them. The same with many features on the moon. The Meton crater I'd mentioned looks like a four-leaf clover. This is my lunar good luck charm. It's made by Meton, wrong direction. Meton CD&E, and I call it my lunar good luck charm. I claim the name. The Guardians, the giant massifs, 1 and 2 kilometers, rising at the mouth of the Alpine Valley, where it empties out onto Mare Imbrium. Chuck Wood named these. And I mentioned Thor's hammer laying on Mare Imbrium, just south of Mons Pico, Mons Piton. Was originally designated Piton Gamma, but those Greek letter designations have been dropped from many lunar features. So the hammer had no name. So I said, okay, it looks like Mjolnir, Thor's hammer. So that's what I call it. The Valentine Dome over on Western Mare Serenitatis, 300 meter high volcanic dome, one of the largest volcanic domes, 35 kilometers wide. It does not look like a Valentine to me, but people have been calling it the Valentine Dome long enough that the name sticks. Cobra Head, the unofficial name of the volcanic pit at the head of Schroeder's Valley. This was the source of the lavas that flowed down the Singer's Rill of Schroeder's Valley. A lot of people mistake Hesiotis crater for Cobra Head, but no, Cobra Head itself is small, no wider than the actual rill itself. So you got to look close. The pyroclastic deposits that cover those mountains north of the Hyginus Rill I mentioned earlier, they look heart-shaped. Therefore, I call this the heart of the moon, because it is almost in the middle of the center of the moon's disk as we see it. So the heart of the moon. And my lunar spider, Lamont, the ghost crater that we had mentioned just above the Apollo 11 landing site, which if you see my cursor is right around here. And then there's Aldrin crater, Collins crater, Armstrong crater, and then the Apollo 11 landing site right about here. And the ghost craters protruding above Oceanus Procellarum down south. I collectively call these the ghosts of Procellarum. And then I have already mentioned why we call ancient Thabit, because it's a very large feature, very large crater, has no name. So let's call it something. And Chuck Wood suggested ancient Thabit, and it sticks. The railroad tracks, I had mentioned those odd parallel rays extending northwest from Tycho crater that do not converge at the middle of Tycho. So don't know who called them the railroad tracks the first time, but we like it, we use it. So in conclusion, before I roll the credits, one final slide mentioning that the moon is not static by any means. It changes hour by hour if we take time to watch. This sequence of exposures taken over a 2-hour period. as the sun rose on Ptolemaeus crater, slowly revealing the interior of the crater little by little, minute by minute, just in the space of 2 hours. So the moon is very dynamic. It presents a different face every time we look at it. So I say the moon is ever changing. The phases grow and shrink day by day. The shadows change hour by hour. The moon is a geologic wonderland. Wonderground could be either. And the moon is accessible from your own backyard. The moon laughs at light pollution. It doesn't care if the lights are on. It doesn't care if your backyard lights on, the porch lights on, whatever. Uh, all the better to see the telescope and operate it by. The moon can be seen uh, from your own backyard anytime it's in the sky. It's generally visible um, uh, for the better part of 3 weeks out of the month. And it's something that you shouldn't ignore because it blots out the deep sky. It's something you should embrace in addition to the deep sky. There's so much to see on the moon, so much geology. It's the only world that other humans, or not other humans, but humans have visited. And in the very near future, we're going back. The Artemis program is slowly creeping along to some sort of um, event where we're going to have people back on the moon again. So pay attention to the moon. There's much to love on the moon, and I enjoy it. I enjoy it so much that I ask you to come join me on my playground. Come out and have fun with me. So I appreciate your attention, and if there's any questions, I'll be happy to take those now.
Let's turn on our speakers.
I got a few questions.
Yeah, hang on. We want to make sure that we're not muted.
Oh, I hear you.
Okay, great.
Okay, I got a few questions for you. I think that your last slide covers or is a good lead into my well, I have three questions. The first one has to do with men, returning back to the moon. You talked about the Cobra head basically as I guess a hole in a volcanic a dome. And I was just wondering, I think if I'm not mistaken, there are other volcanic tunnels or whatever you might call them that have holes in them. And I was just wondering if, in your opinion, that might be a good place for men to visit.
Well, there's been discussion about setting a habitat underground in these pits, these holes, these the exact terminology for them escapes me at the moment, but they're not necessarily volcanic pits like Cobra Head. Cobra Head was a volcanic source for volcanic lava at one point. The things you're referring to, it's literally like a looking through a skylight to a underground cave, and obviously formed by volcanism as well, but perhaps like a paved over lava tube where part of the roof has collapsed. Now, the thinking for using these as a long-term shelter on the moon is there is no atmosphere on the moon, no magnetic field to speak of. So solar radiation and coronal mass ejections from the sun, if you're caught in that mess when the sun goes active, you're a dead man on the moon. There's Back during the Apollo era, they kept a very close eye on the sun with the intention of getting the guys home as fast as possible if something happened on the sun that would endanger them. Now, if you stay on the moon long enough, sure, you're going to get one of these events is going to happen. So the idea is building the habitats underground, protected from these events, and of course meteorite impacts as well. The modern research shows that by investigations by the Lunar Reconnaissance Orbiter and by photography from the Earth, looking for meteor impacts on the moon by staring at the shadowed side of the moon, the dark side that's still in the shadow. We can see these impacts, and we can characterize how often they happen. And impacts, I mean, they're not big enough to create craters we can see from the Earth, but they're big enough to sure tear the heck out of your habitat if we got whacked by one. So we got to get these things protected. So going underground into these volcanic chambers is an idea being floated now, just as a safe haven for long-term stay on the moon.
The next question I have is with respect to the volcanoes themselves. Are you aware of any reports of active volcanism on the moon?
The most recent, let me get back.
Alphonsus.
Yep, there's an Alphonsus in here somewhere,
Yeah.
and I'm going to find it. There. In 1959, Nikolai Kozyrev at the Crimean Astrophysical Observatory captured spectrograms and also visually saw obscuration of Alphonsus by something. We assume it was some sort of volcanic gas venting, but Kozyrev is the only person that saw it, but his spectrograms showed something was there, but has not been seen since. The mystery was so deep that in 1965, NASA even sent the Ranger 9 spacecraft to impact in Alphonsus crater to look for signs of recent volcanic activity and did not see anything. The moon is apparently volcanically dead. If Alphonsus burped back in 1959, it's not something that has happened since. But like I said, the spectrograms definitely show something happened, but we haven't seen anything like it since.
Okay, my final question is with regards to impacts on the moon. Are any of the craters suspected to have been caused not by asteroids but by comets?
Yeah, now there's a lot of them are probably caused by comets. The dynamics of an impact is that a hypervelocity snowball, a comet, will do more damage than a supersonic cannonball. It's just the nature of it. Now, when these things strike the moon at cosmic speeds, 20 kilometers per second, it doesn't matter if it's a solid rock or if it's a snowball. The damage is going to be about the same. What actually creates the crater, excavates the hole in the ground, is it like a bullet hole of something hitting the ground? It's created by the explosion of the vaporization of the impactor when it hits at such a high velocity that the kinetic energy immediately turned into heat, instantly turned into heat so rapidly that it creates an explosion. And it's the explosion that excavates the crater. So it doesn't matter if it's a comet or an asteroid, a rubble pile asteroid, a rocky solid asteroid, at these velocities, 20 kilometers per second or higher, the result is going to be pretty much the same. You're going to get a crater. So I'm sure a lot of the craters on the moon were created by comets, but because of the dynamics of how these cosmic velocity impacts occur, there's no real telltale marker that says, "Oh, I'm made by a comet." So,
Excellent. Thank you very much for your answers.
all righty.
Okay, Steve, you want to unmute here and we're
Yeah.
on? Okay.
Yeah, thanks for this opportunity. Very interesting. I had a question too about lava tubes, but I think you've answered that. But another question I have is about tidal locking. Do we have any evidence from the surface, or is it just by modeling that we know when approximately the moon got tidally locked with Earth?
Precisely when it stopped its free rotation and locked in with the Earth, I have never heard anything definitive about that. But it had to have happened after, or at least very close to the late stages of the Embryon epoch, when uh, the basalt flooded into the basins to create the caricature of the man on the moon, because it is the mass of the basins that is making the moon asymmetrical as far as gravity with Earth is concerned. So it had to have happened sometime late or after the Embryon epoch, which automatically places it as within the past 3 billion years. But remember also that early on, the moon was much closer to the Earth than it is now. The When the moon formed, it was probably no further away than our geosynchronous satellites are now. And once the uh, Earth's oceans formed and tides started occurring, that's when the moon started to migrate away. It is the transfer of momentum by the gravitational attraction of the tides being offset from the Earth-Moon center line that is slowly accelerating the moon. This acceleration is very, very slow now. Um, it's slow enough that it's raising the moon's orbit by about 2.5 centimeters a year. Um, putting that in more practical terms, within a human lifetime, from the time when Neil Armstrong set foot on the moon to now, the moon is about 2 yards further away. So it's a slow process. It also brings to mind how marvelous it is that this process has placed the moon at exactly the right distance from the Earth when humans are here to enjoy it and figure out why a solar eclipse happens. If the moon were closer, the moon would blot out the corona. We wouldn't have a total solar eclipse. In a couple of million years, the moon is going to be further away. All eclipses will then be annular. So when we get this marvelous solar eclipse coming up next April, bear in mind that humanity is here at a very lucky time where solar eclipses can happen. Because in the long-term billion-year epoch time zone, this is a very narrow period of time where a total solar eclipse can happen, as seen from the Earth.
Interesting. I do have a second question, if you can bear with me here, and that's
Sure.
about lunar geologists. I'm wondering if that is a specialty in itself, or is all this geological analysis that goes on, is that just Earth geologists who are just kind of in their spare time looking at the moon as well? Are they real
Well,
specialists?
well, there are specialists, yes. I used to be able to rattle their names off. My gosh, um, but there are those who specialize in that area. But it was initiated by earthbound geologists. The initial understanding of the impact nature of things on the moon was in the late 1800s, when Carl Grove Gilbert, the chief geologist with the U.S. Geological Survey, he became fascinated with the uh, what we now call Meteor Crater at Arizona. Back then it was called Coon Butte, and he speculated that could it possibly have been a meteorite impact, but they couldn't find any evidence of an impactor, so he finally concluded that it was a MAR, something created by a steam explosion, volcanic steam explosion. But that got his curiosity going, and in the late 1800s, he spent 3 weeks at the Naval Observatory in Washington with a 66 centimeter refractor observing the moon, and he noticed the general shape of, I'm wondering if I can get back to a slide that shows that. Oop, there. Mare Imbrium up here, just below Plato. The general shape of it got his attention. And as he studied it more, you don't see them at this full moon phase, but radial to Mare Imbrium here, particularly down in this area here, are radial gouges torn across the moon by the material blasted out by the Imbrium basin impact. We call this these grooves in the moon the Imbrium sculpture. Um, Gilbert saw these and correctly concluded that Mare Imbrium was created by a massive explosion. Now, his analysis was buried in a technical paper that nobody read or knew about for 50 years. And it wasn't until literally the beginning of the space age when politics put the moon in the crosshair of our space program that finally we started looking at the moon again. And it took geologists, not astronomers, geologists, to figure out the true nature of how the moon came into being. So yeah, Earth geologists started this. They understood the moon better than astronomers did, and since then, of course, now we have people who specialize in lunar geology. But it's all very similar to Earth geology. You can have a very good conversation with an earthbound geologist about the features on the moon because there is some degree of similarity.
And Mars is probably a very similar as well to the lunar geography.
Yeah, well, it's no accident that Apollo astronauts trained in volcanic fields here on Earth.
Thank you.
Yeah, so Robert, thank you so much for your interesting talk. I was curious, and hopefully you can help me understand what I might be missing here. You'd mentioned about the volcanoes on the moon and how they were very small. My understanding is that the volcanoes on Mars, for example, are very large because of the low gravity.
This is
Maybe I-
true, and Moon has even lower gravity.
Yeah, exactly.
So that begs the question of why do we have midget volcanoes on the moon, yet Olympus Mons on on Mars is the largest volcano in the solar system. I don't know the answer to that, except I could only guess that the Mare formation process took nearly a billion years. The volcanic episodes, there could be a billion year, million, make sure I get that M out there, million years between volcanic flows. But we're talking in terms of a billion-year span. So eventually the moon flooded the low basins and formed the Maria that we see today. But it was a very long process. The volcanism on Mars may have been more dynamic, more active. It is a slightly larger, it's twice as big as the moon, perhaps more internal heat, um, driving a more forceful volcanism on Mars. This is pure speculation on my part, because the moon is half the diameter of Mars, with a correspondingly, if you crank out the math, the internal volume is considerably less than Mars. So there's less internal heat, less um, um, internal radioactivity to create magma chambers and create forceful eruptions. So the volcanism on the moon was very slow, and I'm betting the volcanism on Mars was very forceful over a shorter period of time, just because the
Okay.
planet is bigger.
Yeah, thank you.
I have a question, actually two.
Okay.
One was, did the Apollo astronauts contribute anything to the geology that you're telling us about? Were any of these discoveries made with the assistance of the data they brought back?
Almost definitely. Remember, I made a point of saying that a T-Rex was probably shook up by the formation of Tycho 108 million years ago. The dating of the Tychonian impact is directly related to the assessment of the placement of Apollo samples returned during the Apollo era. The ages of the Maria I'm talking the time periods of these epochs of geologic time. These are directly related to laboratory analysis of the Apollo samples. Various places on the moon. At Tranquility Base, for instance, Apollo 11, they found basalt samples with vastly varying ages. So it demonstrated that the volcanic activity on the moon was ongoing for a very long time. And of course, these samples that they brought back, they don't necessarily originate within 10 feet of where they picked them up. They could have been thrown halfway across the moon by an impact. But the key figure is that there's such a broad range of when these basalts were formed. So we're able to date the geology of the things occurring on the moon directly as a result of the Apollo samples.
Yeah, I'd forgotten that, but when you mentioned the age of Tycho, I think it was, I wondered how they knew that. Now I know.
Yeah. Yep.
The other question I had is, are you aware of any calculations as to how big these later impactors were, the ones that created the craters that were made in the last billion years?
I have not seen any way to calculate, backtrack. You have a 50-kilometer wide crater. Therefore, if you had a cosmic velocity impact, by cosmic velocity, I mean something traveling at least as fast as the Earth orbits around the sun. I don't know I'm sure it exists, but I do not know myself of the formula where X size crater, what size impactor would it take at a specific velocity to create this crater? If I did a research, I could probably dig it up. It's something I probably should have done when I wrote this here book, but I don't know it off the top of my head. Now that's a little bit over my mathematical capability. I tried to keep this a non-technical book. That might make it a little technical, but it's an interesting point that I should look up, and any modification or subsequent additions to this, that would be a good thing to include. So thank you for bringing it up, although I don't have an answer.
Okay, thank you.
Mhm.
Thank you, Robert. That was fantastic. Great talk. And I'm not sure if you could hear it, but there's a lot of applause at the end.
Oh.
Since you brought up your book, do you want to spend just a minute telling us about your new book?
Yeah, like I said, available on Amazon. Do a title search, Exploring the Moon with Robert Reeves. That's the entire title. And like I said, I did so specifically to separate my book from the other books out there also called Exploring the Moon, which can go back 50 years. It's 300 pages long, 422 illustrations. I say it is non-technical. I do not have any mathematics in it. I do not have any chemistry in it. It's a descriptive walk through the beginning understanding of the moon up through specific observational details that you can hunt down in your telescope. So I'm really surprised at the amount of good feedback I've gotten for this. I with any book, you expect somebody's going to knock you for something on it. That hasn't happened, which really surprises me. Either people are being very kind to me, or by golly, I may have accidentally written a pretty good book. But it's the moon how I wanted to see it presented to me. I've got 50 books about the moon in my bookshelf in the other room, and all of them approached various ways, but none of them did it in a cohesive way that I liked. So I made my own, and I really hope that if you enjoy the moon, you'll consider getting this book. It's available hardback or softcover. Softcover is $39.95. Hardback's $49.95. and Amazon will have it on your doorstep in 2 days.
Hmm.
So if you know anybody who's interested in the moon, here's a good Christmas present for them. So
All right. Thank you very much. Let's have one more hand for Robert. Thanks again, Robert.
thank you very much. It's been fun. Good seeing you again.
Yeah, really nice to see you again too. Thanks for sharing your passion with us. Hopefully I'll
Alrighty.
see you out there.
Alrighty. See
All
you
right,
later.
take care.
Bye-bye.